This is my Physics 2212 Lab 2. This lab was on magnetic field of a permanent dipole magnet. So for our introduction to this lab, the purpose of this lab was to determine the relationship between the magnetic field and an observed distance on and off axis, then apply the Biot-Savart law to understand the dependence on magnetic fields. Finally, create a computational model in GlowScript to determine the results of this experiment. Now, before we cover all of that, we're going to go over some fundamental physics concepts that we will employ in this lab. So first, the concept of magnetic field, which is produced by an electric current. Next, the Biot-Savart law, which calculates the magnetic field of an object observed at some distance r and with some magnetic dipole moment mu. The distance dependence, seen at the bottom, the magnitude of the magnetic field due to a bar magnet, where K is a combination of magnetic constants. This equation is used to solve for the magnetic dipole moments. And finally, the magnetic dipole on and off axis. Now, for the experiment setup, our system is our magnetometer, and the surroundings for our experiment is the bar magnet and Earth. Our initial conditions for this experiment is that the magnetometer and phone are facing north and that the bar magnet is aligned perpendicular to the phone. Next, for our procedure, first we compensate for magnetic north by orienting the phone so that the magnetometer app has an x component of 0. And then second, we find the magnemeter chip by moving the phone up and down the x and y axes. And finally, I followed the procedure for the lab to collect the data for the on and off axis magnetic field at different distances. Here are the results for the experimental part of the lab. We used the distance dependence mentioned before to get a line of regression. Note that the line of regression is decreasing and the slope is a value of negative 2.9922, which is close to the expected since the relationship between the magnetic field is proportional to the r magnitude by 1 over r cubed. We'd expect this value to come out as negative 3. Also, the off-axis magnetic field measurement can be seen at the bottom of this chart. Based on our experiment, we made these two main observations. When the magnetometer is far from the magnet, it measures a near zero magnetic field in the x direction, and as the magnetometer moves closer to the magnetic field, or the magnetometer moves closer to the magnet, the stronger the magnetic field. So for the calculations for this experiment, we use the equation B equals K times R to the N and equated that to the magnetic field of a dipole on axis. And using that, we found the magnetic dipole moment equals the equation seen here on top. Then, using the values from our graph, we could plug those in and get a magnetic dipole moment equal to 2.474. All right, so now on to our computational model. This is the code I used, and I've labeled some of the key parts to help you follow along. So on this one, we have magnetic object and the code for the magnetic field. And then next we have, on the left, we have on and off axis observation location. On the right, we have the code for the magnetic field at on and off axis observation location. And then here you can see that I used a dperp of 0.179, which is used to get an average distance here in our results of 0.253144 meters. And you can see the B at 45 degrees at distance D. The magnitude of B was equal to 2.141138 times 10 to the negative fifth Tesla. And all of our results are here on the right from our code. Some assumptions and the sources of error. Some of these are repeated, but to put them all together, we assume that the magnetometer is properly adjusted to compensate for magnetic north, so there's no influence on B from Earth's magnetic field. Measurements of mu and dperp are accurate. There is no magnetic field contributions from either the magnet or the Earth in the z direction. We always have some human errors and measurements, and then we're also assuming surrounding objects or technologies could cause interference, and we're assuming that didn't happen. So for some questions to answer, for the first one, both the x and y components of the magnetic field would be different because the true magnetic north would contribute to the magnetic field measurements. And then for the second question, the magnetic the magnitude of the magnetic field would increase, but the direction would be the same as before if we had two identical magnets stuck together. Thank you for listening to my lab.